I'm a big proponent of modeling your circuits before you build them, so let's go ahead and jump over to LT-Spice. I've placed a voltage supply here that ramps from 0 to 550 volts. That's what BS is. And then I've went ahead and added the bleed resistor since that's the main component of the circuit we're trying to build. Oftentimes, analog design is like a puzzle. You just add one piece and then you add another and then you add another, checking functionality as you go along. So let's go ahead and run the simulation to make sure our voltage source is what we want it to be. So we look, it goes from 0 to 550 volts and then back down to 0 volts. Let's go ahead and check the current through the bleed resistor. So if we had a supply, the supply connected directly to the bleed resistor the entire time, we'd see 110 milliamps max flow through the bleed resistor. The power dissipated by the bleed resistor is equal to I times V. I went ahead and added the power dissipated on our LT-Spice plot by adding a trace showing the multiplication of the supply voltage times the current through the bleed resistor. We're really concerned about the maximum power that's going to be dissipated. So let's go ahead and look at the 550 volts point on our voltage supply trace and then kind of scroll down and then look at the power dissipated by the resistor at that point, which is 60 watts. Good luck trying to find a 5K 60 watt resistor on Mauser DigiKey that is small enough and cheap enough. Thankfully, we don't need to do that because our parameters is that the bleed resistor loads the supply voltage when it's between 0 and 43 volts. Let's go ahead and look at how we can connect and disconnect the bleed resistor from the supply. I chose a MOSFET that we can voltage control and turn on and off. Some may use a transistor. I like a MOSFET just because it has low on resistance and it's voltage controlled. There's a couple of things we need to look at though. We need to make sure that we know the minimum threshold voltage for the gate to source voltage in order to turn the MOSFET on. We need to see how much power this MOSFET can dissipate. And we also need to look at the VDS versus ID curve, which is going to let us know how much current will flow through the MOSFET when we have a certain voltage applied at the gate and when we have a certain voltage across the drain to source. The MOSFET can handle 600 volts drain to source voltage. Good. We need 550 volts when we switch the bleed resistor out of circuit. A couple other parameters, 20 amps continuous drain current. Won't even need that much. 304 watts power dissipation. I believe when we have 550 volts across the MOSFET, that means we could have a little bit more than 700 milliamps flowing through the MOSFET. Won't even need that, so we're good there. Let's go down to the gate to source threshold voltage. Minimum voltage required at the gate to turn the MOSFET on and get it to start sinking current. We can see that these parameters are tied to some testing conditions right here. 10 volts VDS, 1 milliamp ID. Always adhere to the maximum threshold voltage. Apply more than that, MOSFET will turn on. For a drain to source voltage of 10 volts and a gate to source voltage of 4.5 volts, we can expect just under 5 amps max to be able to flow through that MOSFET. No matter if we increase the drain to source voltage from 10 to 20 to 30 to 40 to 50 volts, the max current is still going to stay the same at just under 5 amps. In order to get more current, we need to increase the gate to source voltage. Went ahead and changed the source to output a constant 550 volts so we can see what voltage we need to supply at the gate of the MOSFET to get it to start turning on and sinking current, which will connect the bleed resistor to the supply. Added a voltage source to drive the gate of this guy, ramps from 0 to 5 volts, plotted the current through the bleed resistor, it's up here in blue, and then plotted the VGS voltage here in green. We can see that the current through the bleed resistor stays at about 0 amps even when we're at the minimum gate to source threshold voltage that the datasheet supplied. When we roll up here to about 4 volts is when the MOSFET starts turning on a sinking current. This is why you always want to design to the maximum gate to source threshold voltage that the datasheet supplies.